Okay, we're going to look at quiz 6 from the fall 2018 semester for Gen Chem 1, and this is covering chapters 3 through 5, or I should say the tail end of chapters 3 through 5. So we're looking at stoichiometry and oxidation states and aqueous reactions and a couple of other topics that are in there. So let's take a look at question 1. It says if you start with 150 grams of iron 3 oxide as the limiting reactant, what is the theoretical yield of iron and the theoretical yield of carbon dioxide? So a couple important things to pick out, right? In this question, it tells you what the limiting reactant is, right? It tells you what the limiting reactant is. So we don't have to go through the whole process of trying to figure out what the limiting reagent is, right? It's already told us, so it's kind of done part of the work for us. So really, this question is just asking how many grams of iron and CO2 can be made from 150 grams of Fe2O3. So we're given information about grams of Fe2O3. We need to convert it into moles of Fe2O3. We're going to compare moles to moles, and it doesn't even specify, right? So we can just leave our answer in moles then, right? It doesn't tell us how many grams, it just says what is the theoretical yield, right? So that's going to be our plan of attack here, right? So real quick, what is theoretical yield? Theoretical yield is just the maximum amount of substance you can make from a reaction, right? In theory, if everything reacted, how much would you make, right? In theory, if you reacted, how much can you make, right? So we can answer that by either leaving things in moles, right? So I'm just going to change my, right? We're going to convert our limiting reactant moles into moles of our product over there, right? And we could also go on and convert it into grams if we wanted to, but the question doesn't specify, so we don't really need to. Okay, so let's start out, right? Let's do, I'll do this step in green, right? Let's do grams to moles. So we start out with 150.0 grams of Fe2O3. I am going to make the assumption that you know how to convert grams into moles. We covered that previously in the semester. If you need some help with that, Fe2O3. If you need some help with that, feel free to look up a video or swing by my office or whatever it might be, right? Converting grams into moles. Let's do this next step in black, right? How do we convert moles into moles? Well, we are now in units of moles of Fe2O3, and we want to get this into units of moles of iron, Fe. And I'm going to put some arbitrary numbers here, right? Completely arbitrary numbers, 1 and 2. Now, where in the world did I get that 1 and 2? Well, it's of course not arbitrary. It's coming from my stoichiometric ratios, okay? It's coming from my stoichiometric ratios. For every 1 mole of Fe2O3, I can make 2 moles of Fe, in theory, right? In theory. So I'm just setting up my ratios. And if we do this math, I got 1.87 moles of Fe. Okay. So there we go. Took care of that one. So if you want to pause at this point and see if you can set up the string of equations for CO2, that'd be some good practice. I'm going to quickly go through and kind of set that up now, though. So again, we start at the same point. We're doing grams into moles. So we convert our starting 150 grams into moles. Moles of Fe2O3. Right? Now we convert moles of Fe2O3 into moles of CO2. And for every 1 mole, we can make 3 moles. Wonderful. And if we follow through that math, I got 2.82 moles of CO2. There it is. A very standard, common, and important conversion to be able to accomplish, right? Convert grams of starting material into grams of product, right? Identify your limiting reagent, and then use that to figure out theoretical yield. Fantastic. Give the empirical formula for a compound, question 2, right? Give the empirical formula for a compound that contains these percentages of those atoms. And so there's a set of steps that we follow to solve these types of percent composition problems, right? So these are percent composition problems. What we do is we can make an assumption of how much of our compound we have, right? That's what a percentage tells us. A percent is, it doesn't matter how much we have as long as the percentage remains the same, right? We could imagine that we have 1,000,000 grams of this compound, and then we just have to take 40% of that 1,000,000 grams. Or we could imagine we have 27 grams and then take 40%, right? But to make the math easy, we just assume, right? We assume that we have 100 grams. So we assume 100 grams, right? And that just makes the math easy. So we have 100 grams of this compound, and 40% of that is carbon. So what's 40% of 100? Well, that's 40 grams of carbon. Okay? And we have 6.7 grams of hydrogen and 53.3 grams of oxygen, right? These are the assumptions that we're going to be working with. I'm just going to spread this out a little bit here. Didn't mean to take that. That's fine, I can correct that. Okay. So the first step is assume 100 grams. Step 2. Grams are mostly useless for us when we're comparing things. We need to convert grams into moles, right? So we're just going to pull our information from the periodic table. For every 1 mole of carbon. 0.008 grams of hydrogen for every 1 mole hydrogen. And we can just say 16 grams of oxygen for every 1 mole of oxygen. Just going to zoom in here a little bit. Okay, we convert grams into moles. And then we work on some ratios, okay? I'll talk about what I mean in just a second. So let me walk through this math here, right? If I do this, I calculated 3.331 moles of carbon. Here I got 6.647 moles of hydrogen. And here I got 3.331 moles of oxygen. Okay, so what I mean by ratio is when we're dealing with a empirical formula, right? Let me get a color here, right? When we're dealing with an empirical formula, we're dealing with the simplest ratio of the atoms in a compound, right? It's the simplest ratio. So we have to make a ratio from our carbon and our hydrogen and our oxygen. So what we do is you divide by the smallest moles. You divide by the smallest answer that you have. Now, it just happens that in this case, carbon and oxygen have the exact same answer. So we're going to divide by 3.331. But when we make our ratios, you divide by the smallest. 3.331 moles. Okay? And 3.331 moles. All right, so I'll just underline this in black just to know where that color is coming from. All right, so we can do some of this math in our head. Right, 3.331 divided by 3.331 is 1. Right, and then 6.647 divided by 3.331. This is equal to about 1.99 something something something. Okay, essentially 1.99. So this is telling us we have a ratio of 1 carbon to 1 oxygen to 1.99999 hydrogens. So 1.999 is really approximately equal to 2, right? We need to have a whole number, right? We need to have whole numbers here. you only round, here's a caveat, right? You only round if the hundredth place, right? You can only round in the hundredth place. Don't round something like 1.25, right? Don't round something like 1.25 to 1, right? Only round in the hundredths place. Don't round in the tens place, okay? So 1.99, very close to 2. So now we have C1, right, H2O1. Or we would just write it CH2O. So we assume 100 grams. We convert grams into moles, and then we divide by the smallest to make our ratios of our whole numbers. Okay? Those are the steps. And only round if it's very, very, very close, right, in the hundredths place. Okay, so write the complete and the net ionic equation for the reaction of barium chloride and potassium sulfate. Now this question assumes that you know your solubility rules for ionic compounds. And remember that solubility rules for ionic compounds are always going to be given to you on the exams and the quizzes that we have, right? And so if you want to pause and look up that information, it's in your book or I posted it online. I'm going to be using those solubility rules in this problem. So first thing we need, right, is we've got barium chloride. We need to know what the molecular formula is, and potassium sulfate. Okay, there they are. These are both ionic compounds, right? It's a metal and a nonmetal, a metal and a nonmetal, or an anion and a cation, right? If they're ionic compounds, when you put them into water, they're going to dissolve, right? So they're going to break apart. So our complete equation starts out like this, right? Our complete equation is where we take the barium chloride and break it apart. So we have Ba2 plus aqueous plus 2Cl1 minus aqueous. We break apart the potassium sulfate, so 2K1 plus aqueous plus SO4 2 minus aqueous. Okay, so the first part of our equation is where we break everything apart. That's the easier part. To figure out what goes on the other end, we have to look at our solubility rules. And we look at our solubility rules and look at what happens when new anion and cation pairs come together. Here's what I mean. We started out with barium bound to chloride. When you mix everything in solution, the positives and the negatives are going to come together. So barium is going to find sulfate. Right? We mix the positives and the negatives. And the potassium and the chloride are going to come together. Right? We make new cation-anion pairs. So you have to know your charges. You have to know your charges for your compounds. Otherwise, you can't really solve these problems. So barium sulfate, right? I'm going to put a little dot here, right? Let's do that in red just to kind of remain consistent, right? I'm just going to put a little dotted line. So barium and sulfate comes together, and oops, let me pause this for a second. I got to change some settings here. All right, so we're back. So barium sulfate and potassium chloride, right? Those are our new compounds that we make, right? I just mixed the purple and the green together. So we have to look on our solubility rules for those purple and the green compound to see if they are soluble or not. If you look at the solubility rules for potassium chloride, the first rule says that all group 1A metals are soluble, right? All compounds with group 1A metals are soluble. Potassium is a group 1A metal, so potassium chloride is going to be a soluble compound. And what that means is it will remain, right, the two potassiums, right, the two potassiums from here, right, in purple, and the two chlorides, right, from here, will just remain in solution. Potassium chloride, if it theoretically would form in this solution, it would immediately break back apart because it's soluble. Right, so it doesn't change. We take a look at barium sulfate, we look at our rules, and it says that, barium sulfate would be insoluble. Barium sulfate would be insoluble in solution. So it comes together, forms barium sulfate, and precipitates out. It forms a solid. Okay, so if you want to pause at this point, pull up those rules and see if you can get to the same point that I did. The next step for us would be to write the net ionic equation. And the net ionic equation is just, there's two ways of looking at it. It would simply be the reaction leading to the precipitation, or another way of saying it would be the reaction without spectator ions. Okay? I'm just going to erase these here for a second, just to clear up things a little bit. If we take a look at our complete ionic equation, we can cancel out ions that exist on both sides of the red arrow, right? And so what do I mean? Well, we have to look for identical things on both sides of the arrow. We have two Cl minuses over here, we have two Cl minuses over there. So in the net ionic equation, we would just have those canceled out. 2 K1 pluses, 2 K1 pluses. The K1 plus and the Cl1 minus, those are spectator ions. Spectator ions. Oops, I forgot to cancel that. There it is. Okay, those are spectator ions. We can't cancel out the Ba2 plus because there is no Ba2 plus on the other side of the arrow. And we can't cancel out the SO42 minus because there is no SO42 minus on the other side. So the net ionic equation would simply be Ba2 plus aqueous plus SO4 2 minus aqueous goes to make BaSO4 solid. Okay, there we are. All right, question 4. Assign the oxidation state for each element or atom in the following compounds. Now, to do oxidation state, there's a set of rules that you just have to memorize. They're in the notes, they're in the book, we talked about it in class. There is no magic to this, right? There is no magic to this. We do have to realize that the sum of the oxidation states for a compound has to be equal to the charge of the compound. Okay? And what I mean is this. So let's start with S8 right here. Right? We'll start with S8. What is the charge on the compound for S8? Well, it's a neutral compound. So the overall charge has to be equal to 0. If there's only one type of atom, aka if we look at this problem, there's only sulfur, right? There's only sulfur, so each sulfur in this case can only be equal to a 0 oxidation state, right? Another way of saying this is S8 is an elemental form of sulfur, and any atom in its elemental form has to have an oxidation state of 0. Right? That's just one of our rules. So any element in its any element in its elemental form has an oxidation state of 0. Okay, now let's go back to the first one there, calcium carbonate. Couple of rules. We have a rule that governs oxygen, and we have a rule that governs calcium. Those are knowns. Calcium, always going to be a 2+. It's a group 2A metal. There are no exceptions to that, right? Group 2A metal is always going to be 2+, unless it is in its elemental form. It's not in this case, so calcium is always going to be 2+. Each oxygen is always going to be 2-. Each oxygen is always going to be 2-. Well, how many oxygens do we have? Well, we have got a total of 3 of them. 3 2- would be -6, right? -6 from the oxygens total, right? We have plus 2 from the calcium. And so we have to figure out, oh, let's do this in blue, right? We have to figure out the carbon in blue here, right? Let's zoom in. Okay, we know the calcium's 2 plus. We know the oxygen total is -6. And everything has to add up to be equal to 0 because this is a neutral compound. Right, so this is the overall charge of the compound. The red and the green are my knowns. And so we just have to fill in what carbon is. And carbon in this case is going to be +4. Okay, so we can write this down here. Got it? Know your overall compound, know your overall charge and find your knowns. And then work your way from there. All right, let's do a couple more examples. Let's hop down here to the bottom, right? Let's hop down here to CO2. Well, we look at it. We know what oxygen is. Oxygen's going to be -2 in this case. That's what our rules say, right? Oxygen's always going to be -2 unless it is bound to fluorine in its elemental form, right? Those are pretty much the only exceptions. We'll talk about a slight exception in just a second, but those are the two most common exceptions, when it's bound to fluorine or it's in its elemental form. There are 2 oxygens though, right? So overall, it's a -4 coming from the total oxygens. The overall charge of the compound is equal to 0. So what is the carbon? Carbon's got to be +4 then again. So carbon +4, right? So the carbon is +4. Just going to box that off there so it doesn't get confused with what's above it. Okay. Moving on to NaH, sodium hydride. If we look at our rules, sodium is our known. Sodium's always going to be +1. If sodium's +1, the hydrogen has to be -1 for everything to add up to be equal to 0. Now this is unusual, right? This should kind of raise a red flag in the sense of hydrogen is typically +1 unless it is bound to a metal. Sodium is a metal, sodium is the +1. Sodium is always going to be +1, right? That's another way of just remembering that rule. Sodium always +1, so the hydrogen has to be -1. But this is a case of what's known as a hydride, which is a hydrogen with a negative charge. All right, moving right along. Here's one that's an easy trick to fall for. Oxygen, we get so used to having oxygen as -2, we stop to think about it. So let's work through this incorrectly first. All right, I'm going to make let's look at this incorrectly first. If we incorrectly assume that oxygen is -2, right, that means we have a total of -4 from the oxygens, which would mean that barium would have to be +4. Barium can never be +4. Barium can never be +4. Go back to your notes and take a look at where oxidation states come from, right? Oxidation states are basically referring to how electrons gain or lose electrons when they form a compound. Okay, that's one way of thinking about it. It's not the best definition, but that's a good definition, right? It's how they gain or lose electrons to get, or how they gain or lose electrons in a reaction to make a compound. The other way of thinking about this is, have we ever seen a barium with a +4? The answer is no. If we pop over to our periodic table, let me just erase some of my notes here that I had from some previous examples. There's our buddy barium right here. A group 2A metal. Let's pretend that barium loses 4 electrons. If it loses 4 electrons, it becomes isoelectronic with tellurium over here, right? Going from 56 to 52. Does that make sense? Would barium want to have the same electron configuration as tellurium? Well, the answer is no, right? It will want to have the same electron configuration as xenon over here. So it would only maximum want to lose 2 electrons. So barium is only ever going to be +2. So this is one of these weird exceptions, right? This is one of these weird exceptions where the barium takes precedence. So I'm going to erase all this incorrect stuff. I just wanted to show you guys, right? Be careful with oxygen. Barium is +2. And if barium is +2, we have 2 oxygens. Each oxygen has to be -1, right? Each oxygen has to be a -1. Can oxygen have a -1 charge? Well, the answer is yes. This is a case where we have something known as a peroxide. Now, peroxide is something you might have heard of before. If you go to the store, you can buy something known as hydrogen peroxide. It's a fairly rare occurrence with oxygen, but we can't have an oxygen with a -1 charge. And that's what's happening in this case. So be careful with oxygen when it is bound to metals. Okay, be careful with oxygen when it is bound to metals. +2 for barium, -1 for each oxygen. All right, and we will just quickly go through this last one here since I don't want this video to get too long, but we can walk through it piece by piece, right? Hopefully you guys can follow along. No exceptions in this case. Each oxygen is -2. Nickel is +2, and the nitrogen is going to be +5. So see if you can get to the same answer that I did in this nickel 2 nitrate example here. Okay. I'm going to zoom out so everybody can take a look at the first page and see if you can get to the same answers that I did.